For more information on tutoring or how to support Moof University and the production of more videos, please visit moofuniversity.com. Thank you and enjoy. If you've got a particle traveling through space, then its location or position is definite at any instant in time. Right? If you throw a ball, it starts at a certain point, and as it's going through the air, and then eventually when it's coming down, at any point, any time, its location is definite. It's right. It could be right here at one instant, and right here, along. It has a certain path that it follows. Okay. Waves aren't like that. They kind of spread out through space. Right. You can't really define an exact location of a wave. Right. And they also diffract. Now there's an issue because electrons have properties of both. Right. They have wave-particle duality. So what does that mean? Well, that's where the Heisenberg uncertainty principle comes into play. The Heisenberg uncertainty principle states that it is not possible to know both an electron's position or location and its momentum at the same time. Right? Momentum is equal to mass times speed, right? Or mass times velocity, but in this case we're going to think about speed. So another way to actually say this is that it is not possible to know both an electron's position and speed at the same time. Okay. So the Heisenberg uncertainty principle can be expressed mathematically like this. Delta x times m delta u is greater than or equal to h over 4 pi, where delta x is the uncertainty in position. The delta is the uncertainty. The x is the position. So x is the particle's position in meters. Delta x is the uncertainty in position in meters. Okay. M is the particle's mass in kilograms. Delta U is the uncertainty, because we have that delta. It's the uncertainty in the particle's speed. Particle's speed is u. That's in meters per second. H is just Planck's constant, which we've seen before. And 4 pi is just a number or constant. It's literally just 4 times pi, has no units. Okay. So there are two variables here, really. There's the particle's position and the particle's speed. Notice that both are not actually in this equation, or in this inequality rather. It's the uncertainty in position and the uncertainty in the particle's speed that are here, not the actual position, the actual speed. Okay. What's the idea here? What's the key? The key is that the more accurately we know one variable, the less accurately we know the other variable. Okay. If we know a value more accurately, there's a smaller delta value, which means less uncertainty. We're less uncertain if we know it more accurately, right? And if the value is larger, if we have a larger delta value, that means we have more uncertainty. So the idea here is that if we know one of these values, one of these variables more accurately, we'll know the other less accurately. Because if we have a smaller delta value in one, we'll have a larger delta value in the other. We'll be less uncertain and more uncertain about the others. Okay, so let's kind of turn this into an actual math problem. Okay, let's use it in a math problem. So let's think about example 1, which is on the atomic scale. Okay, so the problem says an electron moving around the nucleus of a particular atom at a speed of 4 times 10 to the 6 meters per second, plus or minus 1%. Right, so that means this speed within 1%. Find the uncertainty in the electron's position. Okay, so the first thing we do is we write out the actual equation like it is here. Right? Delta x times m delta u is greater than or equal to h over 4 pi. What we're going to do is we're going to solve for what they're asking for. They're asking for the uncertainty in the electron's position. So that's going to be delta x. So we'll solve it for delta x by dividing both sides by m delta u. So we'll have this. Delta x is greater than or equal to h over 4 pi m delta u. So in order to find the uncertainty in the electron's position, we must have h, 4 pi, m, and delta u. So we have h. H is just Planck's constant, which is right there. Okay, 4 pi is just 4 pi. We got that. M is the mass of the particle, so they're asking specifically about an electron, and the mass of an electron is 9.11 times 10 to the negative 31st kilograms. So we got that, and we need delta U. Well, what do they give us for delta U? Well, they don't actually give us delta U. They give us the speed. The speed is U. This is U. This is not delta U. Okay, and they tell us that it's within 1% of this. So what we're going to do to find delta U is take this percentage, and of course it's going to be 0.01, and multiply that by the speed U, which is 4 times 10 to the 6 meters per second. And when we multiply them, that will give us the actual delta U. So that'll be 4 times 10 to the 4th meters per second. That is our delta U. Okay, so now this is what we got here, right? So that's no longer a question mark. But so we've got all those values. We can just plug it in. So delta x is equal or greater than or equal to h over 4 pi m delta U. So we'll plug in h on the top as 6.26 times 10 to the negative 34. Now I'm not going to write joules times seconds, because the joule is 1 kilogram times meters squared per second squared, and that is going to be times seconds. So one of these seconds will cancel here, and we'll get kilograms times meters squared per second. So those are the units that I actually put here for the instead of joules times seconds, so I can actually see the units canceling. Then I'll put 4 pi down here, and I'll put the mass of the electron here, 9.11 times 10 to the negative 31 kilograms. And delta U in meters per second is what we just found there, 4 times 10 to the 4th meters per second. So now these units are going to cancel. The kilograms cancel here. One of these meters cancel. These per seconds cancel. And then all that I'm left with is meters. And the value that I get is 1.45 times 10 to the negative 9 meters. Okay, so that's like a billionth of a meter, right? Which is really tiny. So the question is, this is a tiny amount of uncertainty, right? Or is this a tiny amount of uncertainty? And if you think about it just at face value, yeah, that's a really, really tiny distance. But this is not a tiny amount of uncertainty when we think about what this really is referring to. We're talking about an electron flowing in an atom. So this is actually not a tiny amount of uncertainty. Why? Because compare it to the size of an atom, which we've mentioned that the diameters are on the order of 10 to the negative 10 meters. This value, this delta x that we found here, is 10 to the negative 9 meters, which is actually 10 times bigger than the diameter of an atom. So what does that mean? That means the uncertainty in the position of this electron is larger than the size of the atom that it's in. It's 10 times bigger than the atom's diameter. So what does that mean? That means, in short, it means that we really don't know where this electron is, right? Specifically, it means we can't really accurately know where this electron moving at this particular speed actually is, because it's bigger than the uncertainty is bigger than the actual diameter of where we're thinking about it being, right? So we really have no clue where in that atom this electron is. Okay. And bear in mind, this is because we know the speed, right? Let's think about something on a macroscopic scale and how it compares. Okay, macroscopic scale. So problem here is a baseball, 145 grams, is thrown at 99.9 miles per hour within 1%. Find the uncertainty of the baseball's position. So it's the same idea. We're going to use the same equation here. We're going to solve it for delta x, because that's what they're asking for. They're asking for the uncertainty in position. That is delta x. So that's what we solve for. So it's basically the same as before. It's the same exact situation in terms of what they're asking us to solve for. The difference here is that we have different units. We are given the baseball's mass in grams, so we have to convert that to kilograms. And we're given the mass in miles per hour, which we have to convert to meters per second. So miles per hour, let's convert that. Let's start by converting the hour. So we got 1 hour on top, so the units cancel. That's 60 minutes. And so that'll give us miles per minute if I cancel the hours there. So now we have a unit in miles per minute. Still not what we want. We got to get rid of these minutes. 1 minute on top to cancel the minutes, 60 seconds on the bottom. So the minutes will cancel here. And now we have miles per second. So the per second part is good. We just have to convert these miles to meters. And we'll put 1 mile on the bottom and 1,609 meters on top. That's an approximation, but it's got 4 sig figs, so we're going to roll with it. So the miles cancel, and then we're left with meters per second. So if you multiply this all the way through, what you should get is 44.25 meters per second. Now that's the actual U. That's the speed of the baseball. So we have to find the uncertainty in the speed. So we're going to take the 0.01, right, because of the 1%. We're going to take 0.01 and multiply it by this in meters per second speed, 44.25 meters per second. That's going to be 0.4425 meters per second. And of course, we already have h 4 pi and the mass, which is given here. And now that we found the delta U, we can plug it all in. So h, same as before, 6.626 times 10 to the negative 34 kilograms times meters squared per second. 4 pi, same as before. The mass here, 145 grams, that's 0.145 kilograms, because it has to be in kilograms to cancel. And the speed, or excuse me, the uncertainty in speed, 0.4425 meters per second, goes there. So again, we're going to go through and cancel these units. Kilograms cancel, one of these meters cancel, the per seconds cancel, and we're left with just meters. The answer that we get here is that the delta x is greater than or equal to 8.22 times 10 to the negative 34th meters. Now this is much smaller, right, than what we found before. So is this a tiny amount of uncertainty? In this case, absolutely. Yes. Let's compare it to the size of the baseball. A baseball's diameter is approximately 0.073 meters. So this 8.22 times 10 to the negative 34 meters is way smaller than 0.073 meters. In fact, it's over 30 magnitudes, over 30 orders of magnitude smaller. So that would look like this. Basically one with over, this is with 30 zeros, I think I put here. So it's over that many times smaller than a baseball's diameter. So that's a super, super, super small amount of uncertainty. What does that mean? That means we're really, really, really not uncertain about where this baseball actually is. So it means specifically that we can very accurately know where this baseball is when it's moving at the speed that's mentioned here, right? So what's the point of this, right? Why did I give you one at the atomic scale and one at the macroscopic scale? The point is that on a macroscopic scale like this problem, uncertainty is essentially negligible, right? This value is so small compared to the size of the baseball that we could take it to pretty much equal 0, right? And so because of that, on a macroscopic scale, we can very accurately know both position and speed of a particle. On the atomic scale, however, uncertainty is not negligible. And instead, the more accurately we know position, the less accurately we know speed, right? And also, the opposite is true, or the vice versa, or likewise, what happens, the more accurately we know speed, the less accurately we know position. That's why I put respectively here. Okay? So what, right? Why care? What does this even mean? Why is this important at all? Right? Well, what this means is that we cannot say that electrons float around the nucleus in a fixed path, because we can't actually know its position, right? So that's the idea behind the Bohr's orbits, right? His model mentioned that electrons float around the nucleus in a very fixed path. And that's not the case. That can't be the case, because we can't exactly know the position and speed of an electron at the same time. So instead, we can only comment on the likelihood or the probability that an electron will be in a certain region. And that's part of like the basis for the quantum mechanical model or quantum theory. So I hope that video was helpful. Thank you for watching. If you found that video helpful, don't forget to like, comment, subscribe, and share with friends. Thank you, and happy studying.